All right, chip of the day. In fact, this is going to be sort of a series. This is a 4069 CMOS part. It's out of the 4000 series. And the 4069 is a little bit special. If you noticed here, most of the 4000 series chips that you get will be a B version. It'll be like a 4001B. And the B has significance. We'll talk about that. This one is UB, although it's not always. When you buy these parts, they probably are just marked B. Let me look at the ones that I've got here. Now mine have a UB on them, but usually they'll just be B. But to be accurate, it should be UB. So what does UB mean? It means unbuffered, and B means buffered. So we're going to have to talk about buffered and unbuffered. And but let's talk about the part first, since it's going to be our chip of the day. 4069. It's just an inverter. It's like a 7404, right? So it's just an inverter. And it's a 4000 series, so the voltage range is larger. It says high voltage types, 20 volt rating. So these guys can go up to 100% tested at 20 volts. So yeah, they're pretty cool. And they're very, very simplistic, okay? So here is a buffer, an inverting buffer. It's just whatever you get here is the opposite of what you get here. So positives are negative, negatives are positives. And this is just a up-down thing. So it's very basic, okay? And let's take a look at a buffered part first, and that will help you try to figure things out. Just to confuse things, here's almost the same thing. It's a 74HCU04 unbuffered again, but it's the HC part. And if we take a look at its block diagram, look at that. It's just in and out. It's the same thing. So the 74HCU04 and the 4069s are kind of the same parts. I think actually you can actually swap them. I don't think there's any difference when you use these parts. You can swap them back and forth. All right. Let's see here. What do we need to know? I was going to talk about buffered and unbuffered. Yeah. All right. So we need to know about buffered and unbuffered. I found a couple things here. Let me first talk about buffered and unbuffered. Where's the best? Yeah, maybe it's in here. Okay, I found this paper, a TI application SCHA004, Understanding Buffered and Unbuffered Series, the B and the UB, okay? And they talk about buffered, which are the normal ones, and then they talk about, oh yeah, and there's some unbuffered one too. And here's a list of some unbuffered ones, 1, 7, 9, 11, 41, 49, and the 69. I think they have a good, yeah. So here's a good synopsis of what it means to be buffered and unbuffered, okay? So let's look at the unbuffered one first. So first of all, there's some input protection so you don't zap your CMOS things. So there's some protection diodes and some resistance and stuff. But if you just kind of ignore that part, you just got 2 and 2. So what is this part, okay? So it says it's a NOR gate, okay? So if you think about the output, if you want the output to go high, then this transistor and this transistor has to be on. If you want it to go low, this transistor or this transistor, okay? So these are ands and these are ors. So it's a little bit strange, right? So how does that become a NOR gate? Well, you got some ands and some ors. There was a good picture here. Yeah, here. All right. Okay, so this is a NOR gate, okay? It's an OR gate with a NOT on the output, or inversion on the outputs. This is a NOR gate. How do you build a NOR gate with other parts? Well, you can do you can change the shape and then invert all the lines, okay? That's De Morgan's theorem. And so if you invert the two inputs and you have a NAND gate and then you invert the output, these are the same thing. These are both NOR gates, okay? But this one's buffered. So it has a buffer here, and a buffer here. So the inputs are buffered and the outputs are buffered. So let's go back here, and here is our buffered part. So here's an inversion. Here's an inversion. Those are the buffers on the input, the OR gate, the NOT gates on the input, and here is an inverter on the output. So here's our buffers, and then in here we need to have, instead of a NOR, we need to have a NAND. Okay. So how do you make a high? Well, either one of these is OR. And how do you make a low? Either one of these has to be ANDed. And so that's the way it works. So this and these, you can see these are upside down. This is the NOR gate, this is the NAND gate. And then this one's buffered. And then that makes it into a NOR gate as well. Okay, so if you don't know about De Morgan's theorem, I think I did a video on that once. I don't know. Somewhere back there in my vast collection. Okay, so why do you care if it's buffered or if it's unbuffered? Okay. Well, the buffered one kind of solves some sins. If you have kind of an ugly signal, it's not quite getting up high enough and low enough and stuff, you buffer it and strengthen it, make it strong. So whatever the switch is here, this thing's going to be either hard on or hard off, right? And it's going to create a better situation. So it'll be more intolerant of bad signals, right? This will clean it up, and then this thing will do its thing, but then you clean it up before it comes out. So it's a nicer, robust device. And this one, you know, if the input isn't quite enough voltage, then maybe it doesn't quite do exactly the right thing. And anyway, that's the idea of buffered and unbuffered. Okay, let's look at some of the applications for this part in the back. I think there's a couple circuits back here. Let's see. Yeah. All right. So some of these will look familiar. Some of them will look a bit strange. So a familiar one might be this one. Okay. A lot of times these things will be used as a crystal oscillator, especially like an HC14, 74 HC14, using a Schmidt trigger as an oscillator. Very, very typical thing to do. But actually, you will also see a lot of the, where did it go? The 74 HCU04. Okay, the HCU04, I can't find it now, but anyway, the HCU04 is one of the best things to use here, the unbuffered. Now, why do you care to use an unbuffered part for this? Okay, and that is because if you take a look at the diagram here, it's just a Class B amplifier, right? It's just, you know, whatever you do here, it does the opposite thing on the other side, but it's basically a Class B amplifier. It's going to have some crossover distortion, but it's basically a Class B amplifier, and it will run in linear mode, which is what these parts do, okay? Having this feedback resistor from the input to the output kind of sets the input kind of to the midpoint, and you're taught at an early age, you don't do that with CMOS. You want CMOS either high or you want it low. You never want it in between. That's a bad thing. But that's exactly what you do with these. You set it right at the middle and you use them that way, and it's a good thing. So that's the way these crystals work. If you don't have a crystal, you can just use an RC. And you can just do this. I showed this once before on something. I don't remember. I remember doing this though. So you can have some circuits like this. Today what we're going to look at is this circuit, which is really cool. It is a high input impedance amplifier, and that's what we're going to look at next. We'll try it out. It's just a Class B amplifier. It uses a 10 meg resistor to bias the input, the same as the output, and kind of put it in its middle happy zone, and that's what we're going to take a look at. Let's hook one up and measure it. All right, in the back of the data sheet here, we have a high input impedance amplifier. So it just uses a 10 meg feedback resistor across the part, in and out. Now, I have another document that I found, which is more interesting, which is this one. Also has the 10 meg resistor across input to output. It feeds it with a 1K resistor, which is just there. I don't know why. It doesn't really affect anything. So the interesting thing of this graph are these lines here, the family of curves. It's the VCC family of curves. So if you have a VCC of 5 volts, it acts like this. But if you put in 3 volts, you get more gain but less bandwidth. If you put in 10 volts, you have less gain but more bandwidth. So at 5 volts, it goes out to 100 kilohertz. And then if you go to 10 volts, it goes out to a megahertz. At 3 volts, though, it only goes out to about, just a couple hundred hertz. So let's hook one up. Here it is. So I've got the part in here. I've got a 1K feeding with a 10K, a 10 megohm feedback. I'm AC coupled on the input. And then I'm going to be monitoring 3 things. I'm going to be monitoring the input, the output, and the VCC. Okay, so I'm using 3 scope probes. All right, so I have it set up here. I think everything's going to be about fine. Let's see here. Let's do a 0 on here. Okay, good. All right, so this is going to be our input, our output, and this is our rail here. Okay. Let's break him off, and there we go, that looks better. We'll put him here, and then we'll have input, output, and everything can be big. Let's change our range here to 50 millivolts. Okay, so 50 millivolts per division. Let's turn up the intensity of the grid so you can see it. There we go. And so again, input, output, and voltage rail. So this is at 5 volts. So we're getting about 2x in voltage here. If we change the DC volts here, let's go down 4.8. And you can see this thing's starting to actually get bigger here. Here's at 4 volts. 4 volts, we're getting maybe 4 times the voltage out, something like that. And I think it maxes at 3 volts, so let's keep going. Yeah, look at this thing. Now, it's starting to get very nonlinear, so where the up direction and down direction are not biased correctly on the push-pull thing, or not at the 50% mark. So I think it's very susceptible to the feedback and stuff. And that might be why that 1K resistor helps you kind of balance the thing out a little bit longer. Anyway, here we are. Let's go to 3 volts, which supposedly they had the most. Oh yeah, look at that, we're going off scale. 3 volts. Oh yeah, we're off scale. So let's change the scale here. Yeah, look at that. Wow. So at 3.1 volts, there we go. There's our 3 volt number. And then I think it starts to go down again. Yeah, see? It goes down again. So it kind of maximizes at 3 volts. Don't ask me why. And then at 5 volts and above, it really flat spots above 5 volts. It's kind of the same thing. So anyway, it's very, very interesting. Yeah. So this is a really, really interesting graph. All right, let's take a look at the bandwidth here. I guess we could do a Bode plot on this thing. That'd be kind of weird, wouldn't it? So let's go to 5 volts here. Can we do a Bode plot on this? Let's try it. Analyze, frequency response, enable. Okay, start frequency, we'll start it at 100 hertz, that's fine. Stop it at, let's stop it at 1 megahertz. And input to output, wave-gen amplifier, gain, let's go down to 20 millivolts. All right, let's just do this and see what happens. So it's faster than we thought. So let's limit our bandwidth here. Let's go to, let's see, where do I want to be? I want to be frequency response. Here, I want to do this. Okay, let's start at 100 kilohertz and let's sweep it to, oh, I don't know, 20 megahertz. Let's do that. Let's do that. All right, there we go. So yeah, we're rolling off here. We're rolling off around 2 megahertz, right about there. It's starting to roll off at 2 megahertz. So that's pretty much data sheet. That's pretty good. So let's take the voltage to 3 volts where it had the maximum gain. Let's see, 3 volts there. And then let's do a sweep from 100 hertz to 1 megahertz. There we go. Let's do that one. All right, there we go. Let's make this one bigger because this one's interesting. Let's see, turn these off. Make it bigger. Yeah, there we go. So this one is coming along here. It starts to roll off here at 10 kilohertz. This is the 3 volt one, but much, much more gain. We're getting 20 dB gain out of the thing. So yeah, there you go. My gain numbers don't match the voltage gain numbers on that data sheet thing, so I'm not quite sure what's going on there, but maybe it's my parts. But yeah, there's the frequency response rolling off there. All right, so if you think about it, we've just created a voltage-controlled amplifier. Okay, if you change the VCC, the amplification changes. So we have a voltage-controlled amplifier. It works the opposite way. It's higher at 3 volts than 5 volts, but that's okay. But yeah, a voltage-controlled amplifier. So that's pretty cool. So you can use the pin 14, the VCC pin, as actually a control pin, which is a bit unusual. But yeah, you can do that. It also is a voltage-controlled low-pass filter. Okay? The cutoff frequency changes with VCC. So look at that. This part can do 2 different things: voltage-controlled amplifier, voltage-controlled filter. And yeah, a viewer pointed out to me once a very strange circuit that I believe. I don't remember which one it was either a voltage-controlled amplifier or a shift, a frequency shift thing. Don't remember which, but maybe I can find that again. But yeah, so it's an interesting part. And that was our part for the day. But we're going to do a couple other circuits, so we'll call this the chip of the day, 4069, and we'll do some other funny circuits with this part in other videos.